Hello, good morning. So today is going to be lecture number 21, and we're going to continue our discussions on sequence modeling and hopefully complete it somewhere in the middle, followed by a few slides on best practices. So today will be the last day we'll discuss about like architectures and applications and stuff like that. From next week onwards, it's going to be explainability and different paradigms of machine learning, which specifically are self-supervised learning, active learning, transfer learning, and some introductions into like reinforcement learning and so on. So hopefully by the end of this lecture, we'll just talk about a few best practices that we can do when we are training, we are testing, we are choosing our architectures, and so on. Again, we'll do that after we complete our sequence modeling architectures. So last time we discussed two things, which is RNN and LSTMs. Specifically, they are a case within sequence modeling architectures where the goal is to understand in an online fashion when new data points are coming to us. And basically analyze them and give some sort of a solution to them. We saw a couple of applications, the easiest of which is, again, classification in terms of sequence modeling. So for instance, when we talked about sentiment analysis, so given a review of a movie or a book, our goal is to give a one-word response or classification to that review, saying if it's a positive review or it's a negative review. So those are the kind of applications, or those are the kind of things that we can expect from a sentiment classification setup. But when we have a sequence generation module as our application, that would indicate that given a certain sequence as the input, we expect the output also to be a certain sequence as well. Like the simplest example is something like a visual question answering application where I'm looking at the class, I'm saying how many of you are wearing, I don't know, a hat or a cap or something like that. And the answer has to be something that is based on the visual scene in front of me, right? So this is more of a sequence generation objective that we'll be looking at today within the encoder-decoder architectures. One thing we did not complete last time was the temporal convolutional networks, and I want to spend a few minutes talking about that before we move on to the encoder-decoder architectures. So when we looked at the LSTMs and RNNs, there were a few hiccups or limitations that exist within these architectures. Whenever these kind of input sequence variability exists, it's more difficult to construct RNNs and LSTMs because initially we need to know the number of cells, the LSTM cells, in order to construct these sequential modeling architectures. So TCN is one way that we can overcome that limitation. Next one is about causal sequence modeling. So as I mentioned last time, the word causal is a very loaded thing, especially within machine learning. So if you go and search online regarding causal networks, there's a lot of resources out there that are quite different from what we are discussing within the context of this course. We are looking at the word causal more from a signal processing point of view. As I mentioned on Monday, it is going to be just about the current and the past inputs. So we are only interested in analyzing based on the current and the past inputs rather than anything in the future. And again, it might seem a very trivial and a very intuitive thing to do so. My current analysis and output has to be dependent on what I'm saying right now and what I said earlier, right? So it's very intuitive to think that way, but in most cases it is not. The simplest example can be that maybe what I'm talking right now might not be very apparent to you, but 5 minutes later down the line, if I reiterate the same thing, and at that time it becomes clearer, then you can go back to what I'm saying right now, re-listen to it, and basically that means that you are getting a better idea of the discussions, right? So it's not always a simple process. It's not a very, even though it might be unintuitive, using future inputs to understand what we are saying right now is actually a very common practice in a lot of methods. But since we are talking about one of the more simpler methods, or one of the more simpler applications, we'll be restricting ourselves to this kind of causal sequence modeling, and TCN helps us do this kind of a causal sequence modeling. The optimal receptive field design as well. So this is a very important one. We already know that convolutional neural networks can go very deep. The architectures themselves can go very deep. And this depth is what gives you the higher receptive field. So even based on 3x3 kernels, if I have like 100 layers, for instance, I can take care of an entire 1080p image, and even more than that, even an 8K image, by analyzing them across depth rather than width-wise. So that really helps in increasing the receptive field based on the amount of convolution layers I can construct within my neural network. So all of these provide certain kind of advantages to convolutional networks. So we saw the definitions of what dilated convolution, causal convolutions is on Monday. So today we'll just go through and look what the architecture is going to look like. So given this kind of a kernel, so given this kind of a kernel, let's say a 3x1 kernel, again, we are now talking about a single dimension. When we talked about CNNs before in terms of vision, we always had this 3x3x number of channels as our kernels, right? But currently we are just looking at a single dimension, so it's going to be a 3x1. It is now going to go through the entire sequence. So let's say your blue cells here are the sequences. What we are interested in is doing a 1D convolution on top of it based on a 3x1 kernel. And very similar to what we did with vision, in order to make sure that there's always going to be some kind of an overlap, we need to do zero padding. And this is the two cells that we zero pad at the top, and this is two cells that we zero pad at the bottom. And using that, we can now convolve the entire framework without really taking away too much in terms of the convolution factors themselves. So you can convolve with the first 3 elements, you can convolve with the next 3 elements, and final 3, and so on. And at the very end, what you would have to do is remove a certain number of cells from the top and the bottom in order to construct your convolution, the activations somewhere in the middle, essentially. So very similar to what you did with the 2D convolution during the CNN lectures. So dilated convolution as well is also going to be very similar to this process. A dilated convolution, as we mentioned before, is that there are going to be holes in between where you are not going to consider certain inputs while doing your convolution. So for instance, in this particular case, in this layer, maybe you're looking at every single element in order to construct your output. So all 3 are being used in order to construct one activation. But look at the next layer. This element, this activation is not going to be used when you're considering convolution, right? So you're only going to be using this element, and the last one, these 3 elements, in order to construct this one element within your activation kernels. So essentially what you're doing is downsampling within this kind of a sequence module, not from the input space, rather from the middle representation space. Again, this is for a single channel. This is for a single convolutional channel. Maybe there's a different channel where you'll be looking at, let me get a different color. So you'll be looking at this, and this, let's say, and you have a different set of kernels there that's working. So by increasing the number of channels, you're still making sure that every single element within your activation space is being analyzed, but it's just that now the receptive field is much, much higher. It is in fact twice that it was before you do this kind of a dilated convolution. One thing that we haven't discussed until this point is the idea of weight normalization. So we did talk about something called a batch norm, which is a batch normalization. The goal in batch norm is, and I think we did that when we talked about InceptionNet, and the goal in batch norm was given a, let's say, a mini batch of 32 images. I'm going to pass it through in one iteration within my convolutional neural network, and in the middle of between, let's say, activation functions, I am going to insert this batch norm, and the goal of batch norm is going to be that it's going to normalize my activation. So essentially, I have a set of inputs. I pass it through, let's say, some convolution layer. If I have a batch norm layer in between, that means that the output of convolution, let's call that as our activations, are something like this. This and this are our hidden activations. Right? In the beginning, we always take care of our inputs being normalized. So for instance, currently when you're working with CureOR dataset, one thing that you're doing is to normalize the input batch itself based on some statistics that you're given. Essentially, an ImageNet architecture, its mean and standard deviation was given to you. Something like 0.4 is the mean and 0.25 or something is the standard deviation. You would have normalized your images based on these statistics. But as soon as you pass it through this convolution, right, there is going to be some kind of a mathematical framework that is going to be applied on top of it. So this hidden layer representation here will not have the same statistics as what you started off with in your input. So because of that, there is something called a covariate shift that occurs within this framework. So the goal of batch norm is to bring that covariate shift down. You want to, again, convert it. And the simplest thing, of course, is like a 0 mean and 1 standard deviation. That is essentially what you would have done in this batch norm case. Ideally, you're learning this, but learning this within the gradient descent process. But just from an intuition perspective, you can think of it as 0 mean and 1 standard deviation. So that is what we were doing with batch norm. The goal in weight normalization is, instead of thinking about normalizing the activations, we think about normalizing the convolution kernels themselves. And this is a little bit different compared to the batch norm. So the inputs can remain the way they are as long as we are taking care of the normalization process within the convolutional kernels. And the reason for that is actually pretty straightforward. You want to make sure that your weights themselves are coming from a certain distribution, that certain kernels should not be very large, certain kernels inputs should not be very large. So for instance, if you have a 3x3 kernel, something like this, you expect your weights to be 0.3, 0.2, 0.4, let's say 0.1, 0.15, 0.17, 0.32, and so on. This is fine, at least just by looking at it, it seems fine because it's coming from a normal distribution. But if something is like this, where it's like 0, 0, 5, 1, 0, 0, 0, I don't know, 25, 0, where one of these factors is going to be very, very large. This is not something you want within your convolutional kernel, because one element should not affect your computation by too much. In this case, it will be about 25 times the previous one, right? So in order to make sure that these kind of numbers are not present after my gradient descent process, what we can do is have this kind of a weight normalization process, where W is going to be G multiplied by V divided by norm of V, where G is the new weight vector, and V by norm V is basically the direction of this weight vector. It's a very simple normalization process that we are doing on top of the weights right now, rather than on the batch norm. What has been noticed is that on smaller architectures, this significantly speeds up the stochastic gradient descent process. So you've already seen that stochastic gradient descent is a good process and for deep network training. The reason being that it is inherently noisy, which makes sure that all the we don't get stuck in, let's say, local minima, or saddle points can be overcome by using this kind of a stochastic gradient descent process. But it is a very, very long process, which means that if I want to do 200 epochs on a million data set, on a million image data set, it would take 200 million iterations to complete the process, right? So this is a more difficult process in terms of computation. What has been noticed is that weight normalization helps this process. The convergence basically is sped up in terms of weight norm, and it's also more robust to learning rates. Generally, learning rates are, as you would have seen, it's something of a, you need to understand the training framework and then kind of apply the learning rates. You can start off with let's say, a learning rate of 0.1 and have a scheduler. Essentially, after 100 epochs, you'll make it into 0.01. After 200 epochs, you'll make it into 0.001, and so on. Right? So the goal there is that you know that there's going to be so many local minimas within your loss landscape that you need to decrease your learning rates by a large amount as you go through the learning process, so that you'll escape that learning, that local minima. Weight norm is also more robust to these kind of learning rates itself. So there's a larger range where your gradient descent is going to work, rather than a very fixed setup, let's say, without having a weight norm procedure. Also, batch norm is not good for RNNs and LSTMs because generally when we think of images, we think of it as a mini batch. There's like multiple images in a batch and we use that within a batch norm framework. But in RNNs and LSTMs, we are looking at it from a sequence perspective. So at a single time, let's say we'll have a word, one word within our framework. So the output has to be based on this particular word. The output of batch norm has to be based on this one particular word. And it's not always a good idea to condition our RNNs and LSTMs based on batch norm. And that's why weight normalization is a better framework within this process. So having access to all these elements, our temporal convolutional networks will look something like this. Let me zoom in, so hopefully it's more visible. So we have a dilated causal convolution. This is basically the convolution kernels that we're used to. There's a weight norm. There's a RALU, which is our rectified linear unit nonlinearity, plus dropout. We have seen what dropout is before as well. It's basically this idea that we randomly zero out certain activations so that it acts as a regularizer within our framework. And this entire block is a residual block, which implies that, let's call this as R1. So the output of this will now follow into another residual block, which is going to be R2. Right? So essentially the idea here is that any kind of a computation that is going to be constructed within this one cell is going to be computed another time as well within an R2 in the next stage. And there is this kind of a skip connection from the input to the end as well, similar to how we had within the ResNet architectures within our CNN frameworks. So very similar to CNN. The most important difference, of course, is that this is a 1D convolutional setup, and we have a weight norm rather than a batch norm in this kind of architecture. And it's called a TCN, which is a temporal convolutional network. Any questions about TCNs? All right, so next we come to the last kind of an architectural, last kind of architectures that we're going to be seeing, which is the idea of encoder and decoder architectures. We saw autoencoders when we talked about vision. I believe it was like lecture 18 to 19 or something like that. We saw autoencoders, convolutional autoencoders, and variational autoencoders. In the first one, the simple autoencoders, our goal was just to reconstruct the input. When it comes to something like denoising autoencoders, our goal was to give a noisy input and expect denoised in output at the very end. But we're still constructing the same features as before. The difference in variational autoencoders is that the assumption was that encoder does not need to exist, that there is some space, latent representation space, that if I sample correctly, noise can then be constructed, converted into like a new image or a new data point, right? So those were the kind of autoencoders we had seen. A similar architectural process is what we're going to be discussing right now in terms of an encoder and decoder. Before we get to it, until this point, everything we have discussed, the TCNs, RNNs, LSTMs, can work on any kind of data. We started off by showing heart rate, right? The PQRS phases within the heart rate is something that is a sequential process, and to model that process, we need these kind of architectures and these methodologies. When we come to NLP, which is natural language processing, this is where we are getting more specific in terms of, okay, what we want from our sequence modeling is to analyze language, and the application, if you have data as language, is going to be NLP, which is natural language processing. In this case, we have something called word embeddings that we need to start with. So in CNNs, when we did classification, we took an image, let's say it had a cat in the middle. The goal was to recognize this as a cat, and the way we did it was we trained it based on a one-hot encoding. So we call this as 1, 0, 0. Let's say this is from ImageNet. It would be something like this. A different class, let's say a person class, would have 0, 0, 0, then 1 somewhere, and 0 at the very end, right? So this is how we define classes in vision datasets. But we can't use this kind of one-hot encoding when it comes to these words or within natural language processing. The reason being that the number of words that can exist is a lot. Like if you open a dictionary, think of every single word being used in this kind of a one-hot encoding. So every single word would need a 1 and then all zeros. So let's say, I don't know how many words there are in the English language, but let's say there are 1 million such words. That means that there is going to be million element vector where a particular word will be assigned a position, and then it will be encoded within a position, and that would be a 1, everything else would be a 0, right? And it's very hard to do this kind of a one-hot encoding within this setup, essentially. So what we have is word embeddings, where the goal is that we'll find some kind of a contextual relationship between different words. They might be very different words. Like, so for instance, the word Canada and Ottawa, obviously one is a country, the other one is a capital. If I look at the letters by themselves, they don't have any relationship. C to O, A to T, N to T, and so on. There's no relationship in the letter or a character space, but hopefully there is going to be some kind of a representational space, or let's call it an embedding space, where these words have some contextual meanings between themselves. Right? So that is essentially what we mean by word embeddings. The idea is that there is a latent representation where these words would make sense in close proximity. All these countries and their capitals are going to exist together in this representational space. That is the hope, the idea within this embedding space. Now, if we go back to vision and think of what we are trying to do versus what we had, autoencoders is essentially what we are doing. So autoencoders, the goal was to construct a latent representation space, and this latent representation space consists of some features which are present across different data sets, across different images, right? So there is some kind of a relationship between these features, and this relationship exists, which allows us to construct these images. Same thing here as well. Let's say I have some kind of an autoencoder which takes in Canada, Ottawa, Italy, Rome, Germany, Berlin, and puts it into a representation space where all of them are similar together. So it's going to be similar to an autoencoder framework, and that's why we have an encoder-decoder. But I want to be very clear, an autoencoder, at least in this class, the way we have defined an autoencoder is that an input is going to be reconstructed as its output. That means that if I give Canada, I need a Canada at the very end, right? So the representation space, we have to be very careful in what we want out of our architecture. So we'll be defining something called encoder-decoder, which is going to be different from an autoencoder. The only difference, of course, is that input is not going to be the same as output. Again, think of this from an application perspective. If the goal is machine translation, so I want to translate from, let's say, English to something like German, the words are not going to be the same. Semantically, they're not going to be the same. Maybe the meaning needs to be the same when we do machine translation, but semantically, the words that I'll be using, the letters I'll be using is different, right? So it's not a one-to-one reconstruction about the same characters. So that's why we won't call them as autoencoders, rather we'll call them as encoder-decoder architectures. So some properties of this embedding space that we'll be looking at, it consists of contextually similar words in close proximity. The words contextual can be dependent on the application that we are working on, but essentially, if you're doing machine translation, the words need to be similar between different languages. Those words need to be closer together, even though from a character space, they're they're going to be very different. So encoder-decoder architectures is what we'll use in order to obtain these kind of contextual embeddings. Right, so what does that mean? Let's say take the simplest possible methodologies that we can think of in order to construct these, this embedding space. And this, by the way, these sets of methods are going to be something called word-to-vec, where given a certain word, our goal is to construct a vector, a numerical vector out of it. So that's why the higher class of methodologies is going to be called word-to-vec. The simplest thing you can do is one-word context. Given a certain word, Canada, you want to reconstruct a different word. Let's say it's capital city or something else that you want out of it. And that is the goal. Literally have a simple architecture where you have one encoder. You have this part as your encoder. So this is similar. This is the same image we had used before, by the way, in the autoencoder space. So the only difference here is this is not equal to this. So we don't want the same reconstruction. We can have it if that is the application, but it is not a requirement within this architecture. So given an input word, learn to predict some kind of an output word. So this is rarely used because, again, our goal is to construct an embedding space where contextual similarity is dependent on the proximity of the words in that representation space. So there is an inherent, when we talk about context, there is an inherent relationship between two things. So unless you have those two things, it's not possible to say that there is some kind of a contextual analysis. So while these kind of one-word contexts, it's more of a just to understand what we are doing, but it's never used in practice to actually get these kind of embedding spaces. A better way of thinking about how to get contextual spaces is by looking at neighboring words. So given a single word, the goal is now to construct all the remaining words next to it. Right? So essentially, let's say I am given, I think I have this example in the next one. Let's say I've given the word machine, and this is the word machine. The goal is to construct fundamentals of fundamentals and applications of machine learning. This is essentially what you will be constructing in this kind of an in this kind of an encoder-decoder architecture, where given a single word, machine, you have a single embedding, and from that space you are constructing 3 different decoders. The output of all of these words is the fundamentals then and applications of machine learning. Not the word machine is not there in the outputs, but the word learning is going to be there at the outputs. So this is what we are going to be calling as skip-gram models. There's also an N over there, depending on how many words in the neighborhood you are actually trying to reconstruct. But essentially what you're doing here is, given a certain word, you are trying to find, or you're trying to predict what the neighboring words are going to be. Now you can see, of course, that this is not an easy framework. Machine can exist in many contexts, right? If this was a mechanical class, mechanical engineering, the way that we are constructing this kind of a sentence is going to be very different from a machine learning class. So this hopefully tells you what the word context means. Every word has a context associated with it, and that context, one way of thinking about what that context is by looking at all the surrounding words, or the neighborhood words of the word machine. And skip-gram model is basically, given a single word, you're trying to predict all the other words that occur in the neighborhood. The last way that we'll be discussing regarding word-to-vec is exact opposite. Instead of being given a word and predicting all the neighborhood words, maybe we are given all the neighborhood words and then asked to construct the target word, essentially. And this kind of makes a little bit more sense in terms of trying to understand the context, essentially. So that means, given this phrase, fundamentals and applications of, let's say, dash learning, we are constructing a representation space that combines these the fundamentals, applications, and learning, which is basically the 3 words, and we are trying to get the output to be machine. Right? So essentially, we are feeding in a certain amount of context, and based on that context, we are learning the target word in this particular case. So given these 3 different encoders, we are using a single decoder based on the representation space in order to get our target word. And essentially this idea is called continuous bag of words. Again, It's all within the framework of word-to-vec. All we are doing is converting a word into some kind of a vector, a numerical representation. And the reason we are doing this is because we can't have a one-hot encoding for all these words. And that's why where the word embeddings and word-to-vec comes into picture. And this is like the third methodology of converting words into some kind of vectors based on the fact that we want a contextual embedding space. The intuition here, of course, is that we mask the target word and allow the network to predict it based on the neighborhood words, which is where the context comes from. Any questions about word-to-vec, about the three methodologies within word-to-vec? All right, so word-to-vec is relatively simple in that what we are trying to do is convert a single word into its vector representation, into some kind of a numerical representation. But even last time when we discussed about architectures, when we discussed about LSTMs, which is the long short-term memory networks, we looked at a cell of an LSTM. We saw that there were a few things. There was some kind of a forget gate, there was an input gate, and then there was an output gate. But that by itself was not the entire architecture. Rather, it was basically a unit, a module within that we can use within our architecture. So you should think of that as back when we were discussing resonance, we had a residual block, and that residual block is replicated across an architecture. The cell of so an LSTM cell is similar to that residual block essentially. So same thing here as well. So what we are now discussing is more of an application of how we can use LSTMs and RNNs within our architecture. So here, let's say each of the recurrent neural networks, which is the fact that we have some, if I were to go back and talk about what this is, we have an output that is dependent not just on X, but the current input plus all the previous state, h of t minus 1. Right? So this is the difference between a simple MLP or a CNN architecture, which is, so CNN is something like this, y is equal to f of x, versus something like RNN has this additional block where you have an h of t minus 1, which is the state of the previous hidden layer representation state was used. Correct? So essentially, this block here is doing y is equal to f of x of t, comma h of t minus 1. So given a certain h of t, it is constructing its output. So this is going to be y of t. This is going to be y of t plus 1, y of t plus 2, and so on. At every single instance, there is going to be certain output from your cells. In this case, it's an RNN cell, but you can think of it as an LSTM layer or a LSTM cell as well. So given a certain sentence, how are you? It's converting that into some kind of a hidden layer representation state. So again, think of it as the same encoder-decoder architecture, except instead of each of these encoders looking at certain words, they're looking at phrases or sentences. And essentially your RNN or LSTM is trying to analyze each of these words that is coming in. If it's coming in as some kind of a character, it's pretty straightforward, right? H, O, and W are your x of t minus 2, x of t minus 1, and x of t. And all these inputs are being analyzed within our RNN framework in order to get our output or our solution in this particular case. So the middle representation over here, the Z is usually what we use for some kind of a latent representation. Sometimes we also use H as well. Usually in RNNs and LSTMs we use H, while in CNN Z or CNNs or VAEs, it's going to be Z. So given those kind of representation, our encoder essentially learns what our hidden layer representation is going to be, or our embedding space. And based on that, we need to construct a decoder that is going to output a certain phrase as well. So given the question, how are you? You expect your output, let me increase this, to be something like, I am fine, as your output. You want this as a phrase, right? And that's why we say this is a sequence to sequence. Rather than construct given a certain word, we are getting a target word out of it, or given a certain context, or given a certain word, we are getting back the context of it. The goal is now to construct a sequence that is actually an answer to the sequence that you started off with, which was how are you? And the output in this case is going to be I am fine. So that is the main thing in terms of what sequence to sequence is. And in order to construct the sequence to sequence, it isn't sufficient to have this kind of a simple encoder decoder. Rather, you need RNNs or LSTM architectures, or RNN or LSTM layers within your architecture process. So of course, what we are doing with sequence to sequence right now, the advantage of this is that we are mapping sequences of any length to an embedding of fixed dimension, which basically means that if I want this embedding to be something like 1024 cross 1, it is always going to be 1024 cross 1. It doesn't matter if my input is going to be how are you, or what are you doing today, or which has what are you doing today, which has 5 words, right, compared to 3 words here. Your inputs can have any number of words, either 3 or 5, but your hidden layer representation, your embedding space, is going to have a fixed dimensional space, which in this case is going to be 1024 cross 1. So you are doing a good thing in terms of, you're not saying that your input sequence has to be a particular length. You're just saying that the hidden layer dimensional space, which is the embedding space, has to be a certain has to be of a certain dimensionality. And this is basically what allows you that when you go in and do some kind of prompting within ChatGPT or any other kind of a large language model, you're not limited by the number of words of your prompts, right? You can have, so one of you can ask a prompt in an active voice, the other person can go and ask a prompt in the passive voice, and you'll still expect a similar kind of an answer from this kind of a large language model. So the kind of prompts or the input sequences that you're giving in can have different meanings, or can be different, as long as in the hidden layer representation space, they map within the same context, within the same dimensionality. So this kind of an encoder-decoder architecture works very well on a short sequence. So, but we have already seen that given an RNN framework, or even LSTMs are better, like what we discussed before, but still, they are not as good, and they cannot handle, let's say, a review of a book, or they cannot construct a complete essay given certain prompt. So you would have to go to different kind of architectures, and while these encoder-decoder architectures are good in terms of generating sequences, usually you're limited to kind of short sequences that might exist. So that is the main limitation, which is that decoder must construct, even in this particular case, when you're constructing your outputs, let's say I am fine, maybe your 1024 cross 1 is insufficient in order to construct this output or sequences. And that's very important, because the goal is to construct a contextually relevant answer that is based on the input source, which is whatever the question is going to be, right? So if I have limited my output to be something like just 1024 cross 1, then maybe it is insufficient, especially when my input is a summarization process. So you might have tried this within ChatGPT, but given a big essay or a book, you can ask it to give a summary within a single paragraph. In order to do something like that, it cannot take an entire essay and convert it into this kind of a 1024 cross 1 vector. And even if it does, maybe it has lost out on the important parts. So if the goal is read this essay and answer these questions, let's say you're given 5 questions, the answer to question number 1 and 3 maybe is something that is constructed within the 1024 cross 1, but maybe for questions 4 and 5, it's not present. The answer for that is not present within the summary. So that means your ChatGPT or whichever large language model you're using has failed, right? Which ideally you don't want it to happen. So the goal then is to try to add some kind of an attention process within this language module framework. So what do we mean by attention process? So let's take a very simple, so we won't go deep into attention and self-attention, by the way. Again, this is a fundamentals course, so all we are looking for is more of a motivation into what attention is. So given this question and this figure, so how many people are wearing a plain brown shirt? So this is the question that I'm asking of my neural network, giving two things. I'm giving the input image to it, and then I'm asking a prompt. I'm asking question, how many people in this image are wearing a brown shirt? And the answer is going to be that just one person is wearing it. But think of what this means from an encoder-decoder architecture perspective. So in this case, you are given this, think of for every RNN, you're given a word. So how many people are wearing a brown shirt, right? So that means that there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 RNN encoders that are going to exist. And then you have a fixed dimensional representation space, and your output needs to have, let's say you start off with 20 RNNs, which basically means that you can have a sequence of length 20 in your outputs. In this case, it's 1, 2, 3, 4, 5, 6, 7, 8. So the output is of 8 words. So that means that 8 of the RNNs will have an output, the other 12 will not have an output. So it could be a null character, for instance, or a null word would be the outputs from those RNNs in the previous framework. But the important part in attention is to see which of the words is being output based on which of the source input. So in this question, how many people, if this is where it stopped, how many people are there in an image? Basically, the answer would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 16. So the answer would have been 16, right? The context of a plain brown shirt is what makes the answer as 1. So if I'm trying to answer the question based on the last portion here, the answer that is where the attention needs to be, which is going to be 1. But the initial part of the question is telling me that the answer is expecting number of people, or the question is asking for the number of people, and the answer also needs to talk about it from the perspective of a number of people, which means that one person, the idea of that this number here, 1, needs a certain unit with which it has to be quantified. So in this case, the unit is person, is coming from the initial portion of my sequence, of my input sequence, essentially. So that means that I need some kind of an attention into this process in order to state what the unit is going to be, and I need an attention on this process in order to state what the number or my output is going to be. In other words, this part of the decoder architecture needs to have, let's say, this is where the final thing is, right? So let's call this as shirt. So these two encoders need to influence the first word that comes out, which is going to be 1. And this is person here. How many people? The first few encoders needs to say, or needs to help you decide what the second word is going to be. In other words, the attention for my first decoder is based on a part of my input, which is there at the very end. So plain brown shirt needs to basically go through and say that the answer is 1. So that's where you would need to attend to, while the second word, which is person, has to come from the first part of the phrase, which is how many people. That is where the unit is coming in from, right? So essentially what you're doing is dividing your input into saying that certain regions need to have, so your decoder has to attend to a certain parts of your input in order to say what the answer is differently. So you're not looking at the entire input at once, or you're not attending to it all at once within your decoders. Rather, what you're doing is attending to your inputs at different points of time within your outputs. So that essentially is what attention means, where attention is on the input, but the output, but where it is being used is on the output. So I'm going to create some kind of attention blocks between every single RNS. This is more of a motivation thing. We're not actually creating an attention block, but essentially you can think of it as between every single decoder, there is going to be some kind of a block that is going to have an attention module, and this module is going to be influenced from the encoder part. So it's going to have inputs not just from the decoder part, but all encoders will have a certain amount of input into the decoder part. So that's where attention comes from, and this is a very important word that is used in every single large language model these days. Any question regarding the definition of what attention is? Yes.
So basically, we kind of set the weight for each output of the encoder recurrent neural networks.
Yes, absolutely. So from a motivation perspective, you're absolutely right. Every single output from the encoder of an RNN will have a weight essentially to the output of the decoder of RNNs. Yes. So that also is dependent from a learning process as well. So if the decoder looks at a particular sequence and the convergence has been reached in terms of what the initial objective that was set by the input process, then that means it's done. So it doesn't need to give out any more words essentially. So it's all based on some kind of an objective function. If that objective function has been minimized to below a certain threshold, then that means that it has completely answered the input question.
How do you know if it has converged? If it's approximately if it outputs the sequence that's the same meaning as whatever you have in the data.
Mm-hmm.
So let's say instead of I'm fine, outputs I'm good.
Okay.
Do you expect
So as long as they're as long as they're contextually equal, I'm fine and I'm good are basically the same thing. So during your training process, so I assume your question is during the inference process, but during your training process, you would have set this up. So ideally, you've had enough data where you've asked this question and you have given the answers to be both I am good and I am fine. So essentially what has happened is that it has constructed a distribution from which it has sampled I am fine. Even though we are looking at it as a sequence that is coming out, the representation space here, 1024 cross 1, is going to be something like a normal distribution, one of which is going to be I am fine, another is going to be I am good, and hopefully both of them are next to each other. In this kind of a contextual space. And for this question, either of these answers is going to work. And during training process, it has seen that these answers are going to work. So it has sampled one of these answers to give you the output during the inference time. Yes?
what kind of training data do you use to train a network like this? In terms of like the ground truth and like how does it know what's correct and what's incorrect?
So the simplest large language models, LLMs, only use text. So any kind of a text that is out there. So you can take this PDF, you can take out all the words that exist here and train a model essentially. You can take any research paper out there, any newspaper out there, and you can convert that into just a bunch of sentences, and those sentences are going to go in. They'll first pass through this kind of a word embedding, then they'll pass through these large language models in order to get your outputs. Regarding what the outputs themselves are going to be is a little bit more harder. That is where the design problem comes in. So until this point, we have seen the easiest things. So given a particular sentence, your output can be given a particular phrase, let's say, fundamentals and applications of machine learning. During training time, the goal can be that you have masked out certain word machine and you're just learning the phrase when you're not given the word machine. So this is a very simple way of training, but these days there are more complicated ways. We need to do something called positional embedding, where the position that your word exists within the sentence is what your network, let's say, is going to be calculating. Again, there are many, many different ways, but the training process is not something that we'll be seeing within the scope of this class itself. Exactly. Yeah, exactly. and the context as well, based on what the surrounding words are going to be, and the fact that you know that this word is in the 5th position means that it means something essentially for the network process.
This may be what you're outside the scope, but there seems to be a big leap between giving this algorithm the whole research paper and
Mhm.
giving it text,
Mhm.
and then having the ability to respond to inputs, because the research paper doesn't really like ask question, answer question.
Yes. So there is this, so there's two very important things that has helped us make, as you said, the leap. One is self-supervised learning, and another one is transformers architecture. So self-supervised learning is something that we'll see 2 weeks from now. Essentially, the goal there is that it doesn't matter what your output needs to be, but the underlying structure, semantics is going to be the same. So you can use that in order to construct some kind of tasks which are not the question answer, but basically some kind of different question answer which might not make any sense to us, but help the network learn some kind of a structure. And that structure can be like grammatical from a large language model perspective, or it can be feature-wise, edges versus semantic objects and stuff like that in terms of vision. But it is able to learn these kind of large concepts that it can then use to construct your answers. So even though you're right, research papers don't have the question answers, but the semantics of question answers in a research paper versus something if it has read an exam paper, something like it has seen only questions, are going to be the same. So it can transfer the knowledge it has learned from these kind of question answers, not for that research paper, but for some other domain, into that research paper in order to get the solution. We'll discuss more about that when we come to like self-supervised learning in a couple of weeks. So the simplest way we can actually have attention is by doing a dot product, is by doing a very simple dot product between some kind of a embedding, which is going to be our HFT, with this kind of another vector that we'll define with S of k. And this S of k is going to be nothing more than a very simple, think of it as when we did the forget gate and the input gate, we had this M, N, O, P, right? And we were just doing an element-wise multiplication between the outputs and this kind of forget gate to see what is important versus what is not. This is very similar. S of k is going to be a certain vector, but it's going to have certain values. So maybe the first, after the first word, based on what the first word is going to be from the encoder, that is going to set what S of 1 is going to be. Once you get the second word, that is going to reset S of 1 and it's going to set S of 2. Right? So basically what you're learning or what you're getting from your attention module, your SF1, 2, 3, 4 for the decoder is going to be based on your input, your representation from your input, which is then going to construct some kind of an attention. So the reason we can call this attention, let's say, is again similar to the forget gate. If we have this as 1, 0, 0, 0, then that means the output is going to be completely dependent on the first word that comes out. From your decoder, that it should not depend on anything at all. So in our previous case, when we were discussing this thing, our encoder in the last one, our plain brown shirt, let's say for this particular example, the answer needs to be 1, right? So based on this 1, my outputs would be something like 0, 0, 0, 1, where the final encoded value needs to be the most important one for S of 1, which is going to be the first vector over here. So I need to answer the question, or I need to answer the phrase in the final part of my encoder as my beginning, in the beginning part of my decoder, which is where the S of 1 is going to be. Maybe the second S of 2 is going to look like 1, 0, 0, 0. And that means that the first part of my encoding is the most important one. So when I say how many people, the first part of how many people, I need to answer that within my framework. So this is essentially the simplest way that you can have some kind of an attention module within your encoder-decoder architecture. Again, there are multiple other ways. This was the first and the simplest way that we can go through. In terms of research papers, of course, after this, we have something called transformers, but we're not going to go into transformers since that's a little bit more complicated topic. But similar to what we had when we discussed VAEs, which is the variational autoencoders and diffusion models, knowing what variational autoencoders are and knowing what denoising autoencoders are, it's a linear leap towards trying to understand what something like a diffusion model, and if you've heard of stable diffusion, which is based on these diffusion model, is going to be. And similarly, knowing what this kind of attention and encoder-decoder architectures, it is a linear leap to try to understand something like transformers. But again, transformers is beyond the scope of this particular class, so we're not going to be going deeper into transformers. But when you're doing your projects for the segment anything model, your image encoder is in fact like a transformer, a visual transformer. And if you have the question that, till this point we've just been talking about sequences, and language is a sequence, it makes sense. Speech is a sequence, it makes sense. Heart rate is a sequence, it makes sense. So we can use these kind of sequence models. Transform is also a sequence model, but we use it in images and vision as well. The reason we can use something like that, like a sequence model on images, on this kind of 2D data, is that when we have an image like this, if you take a small patch over here, in convolutional neural networks, the way we do it is we take a small patch, we stride, we move a little bit, and take and analyze on a different patch, right? So this particular patch followed by, let's say, this particular patch, analysis of this is sequential. So the way we consider sequences within 2D visual images is basically based on these patches that are right next to each other, which are sequences. So that basically is what we'll call a visual transformer. But again, I'm just motivating the fact that you can use these sequence models on images. We'll not discuss about what the specifics of visual transformers and transformers in general are going to be. All right, so as I mentioned, this kind of brings us to an end. Yes, question? Yeah. Contextual embedding is what we call what we used to call the latent representation space, is going to be the contextual embedding in this architecture. But there are going to be many architectures where your input is itself not going to be how are you, which are words, but rather they are going to be word embeddings. So you'll start off with some kind of word embeddings as your inputs to your models. So either of those is fine. But in the context of what we have spoken about until this point, this middle representation is going to be the embeddings that we are looking for. Maybe word embeddings is incorrect here. This is more of a sequence embedding rather than word embeddings. All right, so many of the next slides are going to be self-explanatory. It's basically best practices for all these architectures. So we have looked at a lot of architectures. I think from the time, and from the beginning of March, we started off with CNN architectures, and within CNN we had AlexNet, VGG, InceptionNet, ResNet. From those architectures, we moved on to autoencoders, and within autoencoders, there was convolutional networks, fully connected networks, variational autoencoders, and all the sequence modeling that we have done, which is RNNs, LSTMs, temporal convolutional networks, and encoder-decoder architectures, right? So the next few slides are going to cover something like best practices for all of these things. Nothing in the next few slides is set in stone, which basically means that it's a very empirical set of slides. It's not always very clear in terms of what the best practices are, but based on experiences, there are a few things that we know for sure that help us. And those are what has been listed in the next few slides. I won't go through most of these slides because all of them are very self-explanatory in terms of the sentences themselves are you can do this, or you can do this, or you can do that. There's not much of motivation or explanation that are required. So I won't go through it in class, but these are very important from an exam point of view. So these are prime materials for something like a true or false question. similar to what you had in exam 2, quiz 2. So these are the kind of things that you can easily expect. Every single sentence here can be converted into true or false question in terms of best practices. So at the beginning, the first few slides are going to cover which architecture to use. Answer is it's not clear. It's based on application. In classification, of course, it's based on application. And then there's also dense prediction networks. We didn't cover this, but this is how a unit architecture is going to look like. So many of you are working on Tiny SAM, essentially, for your projects. And unit is the one that you have chosen, and this is the kind of architecture that unit is going to that you're basically constructing within PyTorch. It's this kind of a symmetric architecture that takes in an image input and gives you a dense prediction output, which basically means that at every single pixel you have an output. Like classification is very straightforward. You'll just have an output which is a particular class. But in segmentation, for every single pixel, you need an output. So this is where it comes from. Regarding loss function as well, we only look at cross entropy loss or mean square error as our loss, but there are multiple other things, loss functions. And especially when we have this kind of class imbalance, where if the dense prediction is something like this, it's all well and good, right? You have background as your green, you have cat here essentially, and another, is this a dog? Yes, it's a dog essentially. So you have a dog, a cat, and background, all of which are have, let's say, a similar number of pixels. But let's look at the subsurface imaging essentially. Some of you have worked on this data set in your project. But if I were to ask you to detect faults, which basically happens when there's earthquake and stuff like that, and it's very important in terms of earthquake analysis, you need to segment this portion here. This will be red. Everything else will be in a different color. Green essentially, right? So this is a huge class imbalance that exists in real life, and it's not easy. You should not have a simple cross entropy loss that works on this. You need to have something like a weighted cross entropy loss that is weighted based on the number of instances, the frequency of occurrence of these classes, or you can have something like focal loss, which basically weights the difficult samples more compared to the easy samples. Even the performance metrics, if you just simply take accuracy, it's not going to be a good metric, or even MIOU. Again, we have talked about precision recall. This is something that can be very helpful. There was one, when we talked about this kind of a VAEs, there was one question about how do we know if a particular image that has been generated is new. I think at the time I answered the simplest way, at least for MNIST, is MSE, your mean square error, and if it's above a certain threshold, maybe that's a new picture or something like that. But that's actually not a very good metric. Even at the time I'd mentioned it's not a good metric. In more difficult or more natural images, you'll have more different, better performance metrics. One of them is something like SSIM, which is Structural Similarity Index. You don't need to, again, know how to obtain SSIM. You just need to know that this is how your MSE can be very misleading. So this is your original image with MSE. When you reconstruct it using an autoencoder or a variation autoencoder, your MSE is going to be 0. Basically, it's an original image. But if I were to add a certain amount of noise, say like this, versus if I were to add another kind of a noise, say like this, based on different noises, my MSE is still going to be the same. I don't know if you can see it, but it's like 306 and 308, which tells me that this image and this image is the same. Which is completely incorrect. So MSE can be very, very misleading when it comes to these kind of reconstruction applications. So some of the better metrics can be something like SSIM. Look at this, for instance. So this MSE, MSE essentially is the original image minus the reconstructed image, which means that this reconstruction minus this original image has an MSE of 873, which means that this needs to be a very, very bad image compared to this. But look at this. This is like 308 versus this is 873, which is exactly the opposite of what we would expect. Again, these are based on the fact that I can just increase every single pixel's value by 1. I'll get a very high MSE. But essentially what you have done is when you do this kind of a subtraction, the fact that every single pixel has been increased by 1 increases this by whatever the n. So if this is 224 cross 224, then that means that this has now increased by whatever value, 224 into 224, since 1 has been increased. Even perceptually, it's not going to change anything at all. And yet, from an MSE perspective, it is going to change a lot. So MSE can be very misleading. So this is where you need to come up with better performance metrics. For images, it is something like SSIM can exist. But again, we can come up with other situations where SSIM is also going to fail. So it's very important to look at the application and then come up with these metrics. Model debugging, in regression, it was a little bit more simpler. When we talked about regression, we talked about this bias variance trade-off, so low capacity versus high capacity. Same thing, it's more harder to do this in neural networks, and there have been papers which show the opposite. In regression, when our bias was decreasing, our variance after a certain point would increase, and this is when you would know that capacity is an issue. But it has been shown in neural networks that even though bias is decreasing, let's say infinitely, your variance is also increasing infinitely. Sorry, variance is decreasing infinitely, which means that your bias variance, there's no trade-off between the two things, and you cannot use it in order to say whether something is low or high capacity based on just this one framework. Of course, there's a lot of assumptions that go into these theoretical analyses, and because of that, many of these theoretical assumptions don't hold in neural network settings. One of the biggest assumptions we make is this convex loss function, but we know already that it's non-convex and that neural networks are non-convex. And it's very hard to justify simple theoretical measures of capacity on these large networks. Data is also a big thing, and I'm not sure I talked about augmentations when we talked about AlexNet, but essentially, given a certain image, you can rotate it, you can flip it horizontally, add noise, you can blur it, you can crop it, and pass it as a different image. So let's say you start off with 1,000 images, which is very less for training large networks. But now you do these augmentations. You do how many augmentations? 6 augmentations on all images, which means that there are 1,000 rotated images, there are 1,000 horizontally flipped images, 1,000 noisy images, and so on. So based on just 1,000 input images, you can now convert this into 7,000 training images and pass it through the neural network. So this is basically what we call as augmentation strategies, where given a certain image, we can augment it based on some simple transformations that we can do, which is like rotation, horizontal flip, and so on. Because it makes sense, right? So let's say you have an original image of a car. Even if you flip it, it still is a car. So it should be part of the training set with this flipped version as well. So it makes sense to add it as a different image itself. Transfer learning is something that we'll see by the end of this course. Visualization and explanation is something that we'll see by the end of next week. Monday and Wednesday is going to be about this explainability concepts. Activation histograms. Okay, so if I have a very simple architecture, I can look at what the histogram of my activations is going to be. Right? So in our AlexNet, let's say, I have convolutional kernels. There's about 96 convolution kernels in my first layer, each 11 cross 11, I believe. So the output of that is going to be a vector. If I take all those vectors and convert it into a histogram, this blue region is what you're going to see. If I go to the next layer, and I don't remember what the number of kernels are, the output is going to look something like this. So what you'll notice is that after a certain layer, all your activations are going to saturate. At least for this one, which is a hyperbolic tangent nonlinearity. So this was a very famous paper that came out in 2010, where the authors kind of analyzed for deeper networks what these activations are going to be. And talked about it from these kind of activation perspectives. So it's like hyperbolic tangent would look something like this, soft plus nonlinearity would look something like this, and so on. And based on this analysis, they said that the weights of your neural network should not be randomly initialized. It has to depend on some kind of variance, but the weights have to be initialized based on this kind of a uniform distribution with the mean. And so this is U as a uniform distribution with parameters given by this. Again, the math portion of why this is not important. This is more of a for your information part, where in your homeworks, everyone is just doing a random initialization, but there are different ways of initializing your weights as well. You don't need to randomly pick them. This is called as Xavier initialization. Again, this was back in 2010. 10. But since then, since we have started we moved on to ReLU non-linearities. Xavier initialization is not as well used. Timing initialization is more prevalent. Yes. Question? So this first graph is showing you the activation value with respect to the layer. So if I were to draw this, so let's say I have an input image, I pass it through a network which looks like this, which basically is 96 kernel depth, and then 3 cross 3 as the height and width. The output of this is going to be some kind of an activation number, right? So let's say that this is something like, I mean, you guys have already seen this, but if this was a 128 cross 128 image, the output here is going to be something like 125 multiplied by 125 multiplied by 96. So this will be a very long vector of this output. So if I were to take this output and convert it into, if I were to say, let's say the first value is 0.2 minus 0.1, 0.3, and so on. And this is basically this 125 multiplied by 125 into 96. If I were to convert that into a histogram, this is what it would look like. It would be a normal distribution, which means that most of my activations would be somewhere at 0. And there'll be a few activations at, let's say, minus 0.2, then at 0.2, and so on. It's basically a histogram of your activation map. This is showing you that this activation map, it saturates over time, which is not a good idea. But then if you initialize it differently, with this weights, it's not going to saturate. That is essentially what these two graphs are showing you. And ideally, you want something like this. You don't want something like this, which implies that initially you have a large number of activations which are 0, and after that, there's not much difference in your activations. All of them are going to be, let's say, uniform distribution in this case, which is going to be like, there's going to be 5 elements which are 0.5, 5 elements which are 0.2, and so on, which is not what you want. This kind of a normal distribution is better. Yes. 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 This is what the values are going to be after the training. When I think this was done for 300 images, this graph was done for 300 images. When you pass in 300 images, this is the activations. Then finally, hyperparameters as well. It's not always easy to search for hyperparameters. In many of your questions, you're actually given a certain range of values, right? Try it for learning range 0.1, then 0.01, 0.001, and so on. What you're in fact doing in those homework questions is doing a grid search, which basically means that you're decreasing your learning rate in a very straightforward, in a linear fashion. But of course, you haven't done this against batch size, and this matters a lot. I don't know if you're trying to do this now within your homework number 6, but hopefully homework number 7, you're going to do this. There's going to be a Kaggle competition. So you need to do this kind of a batch size versus learning rate setup. And doing this is going to be very hard across a different range of values, right? So many times doing a random search is better for different kind of batch sizes. Maybe a different kind of a learning rate might be better. But yes, so again, these are a small set of best practices. There's no settled best practice in terms of training or inference. This is more of an aggregation from, let's say, different sources. And you might find other sources which tell you exactly the opposite. It might tell you that maybe random search is not good. You need to do grid search. And for different applications, it does make sense. You might want to actually do this kind of a grid search rather than random search. So again, depending on applications, your best practices are not set in stone. But these are good to just start off with. The first thing that you should do is something that we have in these particular slides. All right, so just regarding the course logistics, next week, as I mentioned before, is going to be about explainability. And the week after that, we'll do some kind of an efficient learning. So we'll have one lecture dedicated to self-supervised learning, and one lecture I'll try to do both active learning and transfer learning, or how much ever is possible between the two. And the last lecture, we'll either finish up the previous ones or we'll have introductions, very, very simple introductions to something like reinforcement learning, curriculum learning, and online learning algorithms. I mentioned this before. There's going to be a hard deadline for your project, April 22nd, and there's going to be a hard deadline for Homework 7 as well, which is April 19th. Homework 7, again, will be released on Monday, next Monday. But these are going to be hard, so I will not be able to give extension to anyone because Georgia Tech policy is that we have to give back all your, we have to make sure that there's no assignment submission during the reading period, which means that these are going to be hard deadlines for homework number 7 and project. And a couple of you have talked to me about extra credit, but if you do want to work on extra credit, please email me. Some of the undergrad students who are working on the project, that will be your extra credit. So you don't really need to, you don't need to do anything for extra credit, but for grad students mainly. If you are looking for some kind of an extra credit, then please email me before April 5. Next week on April number 8, I'll announce what that extra credit is going to be along with a set of instructions for the final exam, if it's going to be an exam or if it's going to be an additional homework. Yes? Could you repeat again? So that is what I'm going to be deciding based on the number of people who are going to email me. I'll decide if there needs to be an additional assignment or if there needs to be an exam. So that will be based on the number of people. So if you can email me before April number 5, depending on the number, I'll say exactly that, which is whether you'll have an assignment for extra credit or it's going to be something else, and exam will then be just an assignment rather than the 3-hour exam that you'll do on May 1st. Yes? No, it'll be the same amount as all the other homeworks, which is just south of 10%, I believe. Yes. Yes. So that 20% will be taken over by the homework. Again, for the people who have chosen that. There are grad students who have chosen like full 40% as the project, so they wouldn't have to worry about it. I'll talk about that on Monday, the exact logistics of that, yes. Yes. Based on the number of people who email me asking for extra credit. If there's a lot of people, then that means that I'll just release the homework as extra credit and not as a final exam. But if there's, let's say, less than 10 people who do this, then that means that for them, I'll release a separate extra credit and we can have homework as a final exam. So again, it's going to depend on the number of people. And that's why I'm saying that please email me before April 5. Yes. Maybe we can talk afterwards. Thank you. That's the end of the lecture.